Hi everyone, going to talk about a bit of mutual exclusion and synchronization today as a review. Before I do that, a bit of context. When we run a program with multiple threads, we first can think of threads as virtual cores. What does that mean? By running multiple threads, we are giving our system the illusion that we actually have multiple CPUs, each running their own program. However, when we only have one CPU, how do we actually achieve this illusion? Well, we create a structure that tracks the state of each virtual CPU, each thread, and potentially interleave or schedule these threads to run at different times and different amounts. So when a thread is chosen by the scheduler to run, we store its registers into the processor, and it's like we're using a whole new CPU. And so when we have multiple threads running concurrently, which means we may have threads that are running, or let's say we have three threads in the program, A, B, and C. A may run for a little bit, then the scheduler switches to running thread B, and then maybe it switches back to A or C. So we have this scheduler that chooses the next thread to run and may interrupt the running thread to switch the currently running thread. And until we learn about scheduling, you can kind of assume that the scheduler randomly interleaves these threads, randomly picks when to switch the threads and for how long they'll run. The only non random part that you are um, going to assume is when you have certain functions that um, block a thread or put it to sleep, like we'll talk about in a bit, or also when a thread is blocked on I/O. Okay, so with a multi-threaded program, we have this concept of cooperating threads, which means we have threads that are sharing data with one another. And if we um, have this mechanism of interleaving threads where thread A runs for a little bit, then thread B runs, etc., we want to make sure that any threads that are sharing data don't have any race conditions with actually updating that data, which is thus the actual point of synchronization and the end of my prelude. And so to actually achieve synchronization, we use something called atomic instruction or operations. Sorry. So atomic means that the operation either runs to completion or not at all. And if the processor had no atomic instructions, you can imagine it would be very difficult to eliminate race conditions because you can no longer assume that any instruction you execute is guaranteed to actually complete. Um, yeah, that's kind of a weird way of saying it, but also keep in mind that an atomic operation does not necessarily mean it's an instruction. Um, and we'll see like the example in a little bit. Okay, so yeah, mutual exclusion is just a term describing this idea that we want to prevent more than one thread from doing a specific action that would interfere with other threads' execution. And so we're going to mutually exclude things so that only one thread gets to run a critical section of code at a time. So the thing that you're excluding is the critical section. Um, yeah, and so we refer to the code that runs as part of mutual exclusion as the critical section. And we're going to build a way to make the critical section of a thread's execution run uh, atomically on a shared state. And I say atomically in air quotes that you can't see because we're providing an illusion that the section of code runs atomically, even though the code section itself is not actually atomic. We're going to provide this illusion of atomicity. I can't say that word. Um, we're going to provide an illusion that it's atomic, as we'll see in later slides. Okay, so now we introduce the idea of a lock. And similar to how it sounds, when one thread holds a lock, no other thread can hold it. So we create two atomic operations, acquire and release. And we are going to define the critical section as the section of code that's in between a call to acquiring and releasing a lock. And so normally the critical section will modify some shared state, and that's why you protect it with a lock. So only the thread that has currently acquired the lock can modify that data at a given time. And if we take an example from our word count homework, if we have a bunch of files for which we want to create a frequency map or a list of the words across the files, we spin up a thread for each file, and when thread A wants to add a word to the list, it makes the code that reads and writes to that list a critical section by wrapping it with the lock acquire and release. And so now any other thread that tries to acquire the lock before modifying the list will have to wait for the previous thread to finish adding its word and give up the lock. Okay. And just a note that this sometimes becomes a point of confusion. A critical section of code does not mean that it runs uninterrupted. So the thread that runs a critical section may be interrupted in the middle of it, but that critical section is still protected because any other thread that tries to acquire the same lock and then run a critical section related to that lock is going to be blocked from acquiring the lock until the original thread releases it. So um, if you have like a critical section of code that should be or that is protected by a lock, and let's say modifies some shared data, and then another thread you modify that shared data without trying to acquire the lock, that breaks the whole point of using the lock and of the critical section. So it's basically up to the programmer to make sure that you're properly using the lock such that any part of code that's modifying shared data is only executed after acquiring the lock and that the lock is released when the critical section is done. Okay. And so semaphores. What are semaphores? Semaphores are like integers with some key differences. So there are no negative values. A semaphore must be non-negative, and they cannot go below 0. And you only have two operations. You have down and up, or wait and post, depending on like what library you're using. So when you down a semaphore, uh, the thread that calls sema down or sema wait is going to wait until the semaphore value becomes strictly positive, and then decrement the value by 1. So if the current internal value of the semaphore is 0, down or wait is going to block. Up doesn't have any blocking, it just increments the value of the semaphore by 1. And so a mutual exclusion workflow of a semaphore is very similar to what we talked about with locks, where you can initialize the semaphore to 1, which in this case is basically initializing it to free, as you do with initializing a lock, because the first thread to call sema down, or the first time a sema operation is called that is sema down, we're going to be able to successfully down the semaphore to 0. And then you can down the semaphore when entering a critical section. That means that any other thread that tries to down the same semaphore is going to block until step 3 happens, which is the initial thread ups the semaphore, or any thread that ups the semaphore is going to allow a thread waiting on the semaphore to unblock, basically. And now, the more interesting workflow that you can use for semaphores is scheduling. If you want, let's say, thread A to wait for thread B to execute some code, you can initialize a semaphore to 0, share the semaphore among these two threads, and the thread that you want to wait for something to occur, you're going to down the semaphore. So in this case, if A and B have a shared semaphore, we want A to finish or to wait for B to finish executing. In A, we immediately down the semaphore, and in B, after we do our work and finish running whatever we want to run first, we up the same shared semaphore so that when the scheduler switches back to A, or switches A into execution, the sema down will finally unblock and we can continue executing whatever code is after the call to sema down. Okay, I'm going to skip the examples from discussion for the sake of time, but just a quick overview. So when we have this bank account transfer problem, the reason we have this like diagram on the right is, as we said, if we have one thread running transfer Alice Bob, another thread running transfer Bob Alice, The scheduler may switch the the initial thread, which is transferring from Alice to Bob, may switch that thread um, to now run the other thread that's transferring from Bob to Alice. And so you may end up with some weird interleaving of these two threads where part of the initial transfer executes, then we switch to executing um, the other thread that transfers from Bob to Alice. Maybe we entirely execute that transfer function, and when we switch back to the initial thread, there's one more um, or one more operation that we didn't finish. But at this point, the state of our program has changed because we're sharing data among these threads. So that wasn't said super eloquently, but hopefully that makes sense. And yeah, I'm going to skip just to condition variables. The rest of this is mostly filmed. Um, okay, so condition variables. These are arguably a bit more complex than semaphores and locks, um, although locks are involved and semaphores are technically involved. But condition variables are synchronization variables that let a thread wait for a change to a shared state. And very weirdly, we allow threads to wait inside the critical section using condition variables. Now, this sounds very strange. Based on what you saw previously, you might say if a thread is sleeping inside of a critical section, isn't it holding a lock? Isn't that the point of a critical section, that it's holding some lock that someone else might wait for? How is it going to wake up if it's sleeping in a critical section? And if it doesn't, won't we achieve deadlock potentially if someone else tries to acquire that lock? Well, there's a catch here, which allows us to actually sleep inside the critical section, which is, I guess we'll see in the next slide. But the first thing that we do with condition variables, and typically we'll refer to monitors, which is a lock with 0 or more condition variables. And so one operation that I just talked about is wait. So if you wait with a condition variable, or you call cond wait, um, what's going to happen is you atomically release the lock that you previously acquired, and you block the current thread. You put the current thread to sleep. And so, as we'll see in the following slide, when you're using a condition variable, typically you have an associated lock that you first call, or that you first acquire. Then you call one of these three functions that you see here: wait, signal, or broadcast, and then you release the lock. So keep in mind, before you call one of these three functions, you acquire the lock. And the reason that we are okay to sleep in the critical section is because after we acquire the lock, maybe we have some lines of code, and after that, we have a call to wait. Now, keep in mind that all of the lines of code between um, the lock acquire and con waits, all of those are protected because we have acquired the lock. Now, when we call con waits, before we actually go to sleep, we release the lock so someone else can acquire it. And so signal and broadcast are going to wake up the next waiting thread in the queue. What does that mean? If in metasemantics, and we'll discuss what that means in a second, but in metasemantics, we when we signal a thread, we're going to take a waiter, the next waiting thread, mark it as ready. So we're going to change that thread from being blocked to ready. And so the scheduler, when it goes to schedule the next thread, can um, choose the newly woken up waiter to run because it's unblocked. Broadcast is similar, but it's just going to wake up all waiting threads. And to avoid further confusion, I mentioned this term metasemantics. What does that mean? So condition variables can work one of two ways. Metasemantics is what we discussed before, where when we call signal, um, we're just going to put one waiter on the ready queue, but we keep the lock until explicitly calling lock release. In horse semantics, when we call signal with a condition variable, we signal a waiter, but we actually immediately give away the lock and the CPU to that waiter. And so there's a difference between this atomic transfer of the lock and the CPU in horse semantics versus in Mesa, once we call signal, we just mark a waiter as ready. That doesn't mean that we actually run the thread or schedule it or anything. Um, so yeah, that's a very important difference. And the other one is that because of this assumption, or because of this mechanism, when we have some clause, some condition that we're waiting on, so in this case of the buffer, we have this if machine is empty. Um, in horse semantics, we have an if statement. And in Mesa, we see that this is actually a while. And the reason that it's a while statement instead of an if in Mesa is because when signal is called, recall that the next waiter is just put on the ready queue. Between the time that the waiter was signaled and actually ran, the state of our program might have changed because there's some gap in between um, those two events. And so if the machine is empty again by the time our waiter is actually woken up, right? Like our waiter was put on the queue when the machine was no longer empty. Maybe then the machine was emptied out again. And so by the time that um, we return back to this waiter, the machine is empty again. In that case, we want to go back to sleep. So we check this condition. If it's true, we go to sleep. When we wake up, we check and make sure that it is definitely not true again. Otherwise, we have to go back to sleep until someone wakes us up. So yeah, um, this is very important. And then similar to what I mentioned before, so when you're performing a condition variable operation, make sure that the thread is holding the corresponding lock. And here, there is no lock acquire, and there's also no initialization of the locks or condition variables. Anytime you're using a lock, condition variable, or a semaphore, make sure that you are initializing them with the corresponding functions. Here we're using the pthread library, so you would have like pthread cond init. If you're using Pintos, you would have just like cond init. Um, the exact like spec will typically be specified. Okay, so I'm just going to go over this example really quickly. This was intended to be like a shorter video, and I am incapable of that, so it is long. But what we want to do here is make this program always print yeet, yeet ha. Okay, and so we see when does that get printed. That gets printed if this variable ben is equivalent to 1. And we see ben is a global variable. So when we create this thread that runs helper, ben is the same ben as in main. Okay, so this clause that we want to always print eta means that we want helper to execute before we get to that statement. And so if we're using condition variables, first we see that with any use of the condition variable, first we acquire the lock. When we're done with it, we release the lock. So that's the first two, or the first and last bold lines here. And in terms of signaling, when after we increment ben, and that's the condition we are waiting on in the main thread, we are going to signal the corresponding condition variable. So where is or what is the signal doing? Well, in the main thread, we're going to check if ben is still 0, or if it's just not 1, and then we're going to wait on the condition variable. Once helper actually runs, it's going to signal that condition variable, and so the wait is going to, or the call to wait will be unblocked, basically. The main thread will be put back on the ready queue, and once main runs again, we see that ben is equal to 1, and so we print eta. I think this is kind of a confusing example of why you would need to set or have this while loop. But if like you had multiple threads that are running helper, or let's say you have one thread that's running helper, maybe two that are running helper, and another that's running another function like decrementing ben, then you could have some more complicated system that um, when you wake up, you being the main thread, you actually need to check that Ben is indeed um, one, and you don't need to wait anymore. Yeah, that was not said very eloquently, but um, we'll look at more examples in the walkthrough that I hopefully post in the morning. So yeah, let me know if you have any questions, and see you later.